Hello, welcome to Unit 1, Day 1, Introduction to Statistics Notes. Your learning objectives for this video or this lesson is to identify the components of data displays. So that includes display, range, and intervals. To determine if display data gives a misleading impression, and then also to distinguish between causation and correlation and identify a possible lurking variable. Now, this last objective we have actually already talked about back when we did statistics in Unit 3, but it's always a good idea to kind of revisit some ideas. So we're just going to go ahead and review that. All right. So let's go over some vocabulary. So data. We're going to be talking a lot about data in this unit. So when we're talking about data, we're talking about things that have been collected and they are used for analysis and reasoning. So these are collected facts used for analysis and reasoning. Now, data can be both quantitative in nature or qualitative. So, quantitative or qualitative. So, quantitative, we're talking numbers, 1, 2, 3, 4, things like that. Qualitative, we're talking more like categories. So, what's your favorite ice cream? What's your favorite color? What's your favorite pet? Things like that, where you're not going to be giving numerical answers. All right, so the other vocabulary word is range. So you may or may not recall, but range is the difference between the highest and lowest value. Range is often used to describe how much the data varies from each other. So just keep that in mind. Now, data can be displayed many multiple ways. Some of those ways include as a histogram, as you can see below, dot plot, box and whisker plot, or also known just as box plot. You can also have a bar graph, circle graph, etc. So there's just many different ways to display data. So let's take a look at our first type of data display here. We have a histogram. So just a general description of a histogram. It kind of looks like a bar graph. The thing about a histogram is that it's working with intervals. So when we draw histograms, our bar graphs should be touching because the intervals are continuous, so they never stop. Histograms are used with numerical data, whereas bar graphs typically are used with qualitative data. In this specific histogram, we're looking at intervals of 5. So our first bar goes 1 to 5, our second bar goes 6 to 10, our third bar 11, 15, and then so on. Now, figuring out the range is a little bit more difficult because we don't know the exact data. All these bars tell us is that, for example, here, this looks to be about 4, right? There were 4 pieces of information that fell between 1 and 5. Here, this looks to be about 30. There were 30 pieces of information that fell between 6 and 10. But we do know that the highest we could possibly be is 25. The lowest we could possibly be is 1. So our range would just be 25 minus 1, which is 24. So it does have a range of 24. Now, our dot plots, you can use this with both qualitative and quantitative data. In this specific dot plot, we're looking at qualitative data. We're talking about the number of different types of snakes at a school. So in this case, there's not really an interval of data because we're talking about qualitative data, so no interval. And again, because there's no intervals, there's no range. Now the last example we have is a box and whisker plot. It doesn't have any context to it, it just has numbers. We can look here, we see the intervals are 5, so that, and the range goes from 100 to 65. So when I subtract those, I get a range of 35. So the data ranges by 35. Now, when it comes to data displays, the one thing about statistics is that sometimes your graphs can be very misleading. So good graphs are extremely powerful for tools for displaying large quantities of complex data. They help summarize conclusions easily. However, some graphs can deceive or mislead, and sometimes people will actually do this on purpose because when they give presentations, people are not well versed in knowing what graphs should look like. So they can deceive them to make the data look like something in their favor. So our goal is to teach you how to recognize when a graph might be misleading or deceiving. So let's take a look at some different graphs and see if we can recognize why it might be misleading or not. So let's look at this first graph. If we look, it's a bar graph, and we're talking about the increases in house prices. In 1998, we have this short little bar that shows that there was an $80,000 increase in house prices that year. And then a year later, we can see there's a bar that's more than double. So this bar is more than double the previous bar. And it shows that the housing price increased by 82,000. And we're not talking about dollars, we're talking about pounds, so I shouldn't misspeak. But because that bar is more than doubled, we would expect that the housing prices to also be more than double. So that can make it very misleading. And the reason why it's misleading is because the bar graph does not start at 0. Does not start at 0. If it started at 0, there wouldn't be that significant of a difference between the sizes in the bar. But because they cut it off and they actually are starting closer to 80,000, it does make it appear like that in 1999, there was a significant increase in housing prices, which in reality, there was only a $2,000 or pound difference in housing prices. And that's really not that much in the grand scheme of things. So this can be very misleading to people. All right, let's look at the next one. So this one shows a line graph, and in analyzing it, there's no context. We're not sure what's happening here, but we can see there's a pretty steep increase here, and then it kind of slows down, right? It goes from 0 to 8 in a matter of one interval. So maybe that's 1 year, 1 month, whatever. The next increase shows in between an interval is that it only jumps up two lines. But if you look at that, it goes from 4 to 16 in that interval. Whereas here, between 1 and 2, we only went from 0 to 4. And so in reality, that line should be less steep than the other line. because the interval is much smaller. And why is this misleading? Is because they're not using consistent intervals. Let's say they use the same intervals. Let's say they went up by 4s, right? 4, 8, 16. If they went up by the same intervals, then we would see that that original 1 to 2 gap, this gap right here, would be less steep than the gap right here. So by not using the same intervals, they are making it seem like that it's significantly steeper between the first two on the y-axis. Now, the other thing that can be misleading about that is there's no labels or title. We don't even know what this graph is about, and it made it kind of hard to analyze it. So misleading graphs, when you don't have those labels listed, it can be very deceiving. All right, let's take a look at the next one. So this next one shows kind of a 3D bar graph. On the y-axis, or sorry, the x-axis, we see it looks like it appears to be number of years. And then it's kind of going on an angle. Now, there's no y value, so that's the first thing that there's a problem with, no y value. So we don't even know what the height of these represent. And the other thing is that the angle that it's going off makes it very misleading. One of the things that maybe you've learned in art is that idea of perception, right? And as things get farther away, they naturally get smaller. But in reality, they may not be smaller. They may actually be bigger. So the angle on this graph it can make it very deceiving in the sense that maybe this last piece is the same size as the 1996. So angle makes it deceiving. It's just because we don't know that perception that's happening. All right, let's look at the next one. So here we have a pictograph. Again, right, we have no labels. We don't know what we're even talking about here. Are we talking about ounces? Are we talking about volume that it holds? Are we talking about the circumference of the top? Are we talking about how tall it is? So no labels can make it deceiving. And the other thing that makes it deceiving is that the pictures are not proportional. And what do I mean by that? Well, let's look a little bit closer at the height of each one. So the height of this smallest one is 100, and then the height of the biggest one is about 250. But look at the overall sizes of the picture. This height of this last one is only 2.5 times bigger than this picture here. But the overall size of the picture is about 4 to 5 times bigger, right? I could probably take 4 of these and fit it inside that big picture. So the pictures are not proportional to what it's measuring. In reality, if we're talking about a height difference of 2.5, right? We went from 100 to 250, that's multiplying by 2.5. Then my size of my picture should only be 2.5 times bigger. So some things to keep in mind when it comes to graphs is that a graph can be altered by changing the scale of it. For example, if we look at these two graphs that are identical, we can see that the scaling on the y-axis give us an impression of a magnitude and difference. And this kind of matches back with what we said in the first example. On the left, our intervals are starting at 0, going up by 1, but on the right, it starts at 4, and they still go up by 1, but it makes it appear that the second and third graphs are significantly bigger than the first graph. But if you look back at the our graph on the left that starts at 0, there's really not that big of a difference. So that magnitude, it does really make a difference. So a few ways that graphs can be misleading. Scales do not start at 0. So if you look back at example 1, we can see that that's an example. Scales are made very small to make the graph look big. So you can look back at example 1 for that as well. When a scale is not consistent, that can be misleading. So that's example 2. And then scales values or labels are missing from the graph. You can take a look at examples 2 and 3 for that. Now, this next part I want to talk about is that correlation versus causation. Again, this is a review. We've already talked about this in the past, but, it's a good idea to review because it's been a while. So one thing to remember when it comes to correlation versus causation is that correlation does not necessarily mean it causes causation. It does not imply causation. So remember, correlation is a statistical way to measure the relationship between two sets of data. It means that both things are observed at the same time. So meaning as something increases, the other decreases, or as something increases, they both increase. Something's happening at the same time. Data can have a positive relationship, so meaning as one thing increases, the other also increases. It could have a negative correlation, so as one thing increases, the other decreases, or it could have no correlation. And if you recall, we determined this by looking at these R values, the correlation values. Now, causation means that one thing will directly cause the other to happen. And if there's no causation, we can identify a possible lurking variable. If you may have recalled, we watched a video that talked about how during the summer, when sales in ice cream increases, we also see an increase in forest fires. Now, that does not mean that ice cream sales cause forest fires. Instead, there's that lurking variable. And we talked about how the lurking variable is the temperature. Ice cream sales likely increase when it's warmer and hotter, and that also means that forest fires are likely to happen. The temperature gets warmer, so therefore we're going to see more forest fires occurring. So let's go ahead. What I want you to do is pause the video and try to determine if there's a causation or no causation for each of the following examples. And if there's no causation, I want you to go ahead and see if you can identify the lurking variable. All right, let's take a look at the first one. In research, findings show that the higher the number of volunteers that show up after a natural disaster, the greater the damage. Therefore, more damages occur because of volunteers. Now, we know that this is not causation. What's happening here is that it's actually the other way around. In a natural disaster, more people show up because there is likely to be more damage to help clean up. So in this case, our lurking variable is actually going to be the natural disaster, right? The natural disaster is what's causing more damages, and because there's a natural disaster, we're going to have more volunteers. Now B, a survey shows a strong positive correlation between the percentage of a country's inhabitants that use cell phones and the life expectancy in the country. Therefore, if a person uses a cell phone, they will live longer. Again, obviously, no causation. And in this case, the lurking variable is how developed that country is. Countries that are more developed have access to better doctors, and they often have more money where they can buy cell phones. So, how developed a country is. Third world countries, they don't have a lot of money, they don't have a lot of access to doctors, and they don't buy a lot of cell phones because their money goes more towards necessities. All right, C. There's a positive correlation between the weight of a Thanksgiving turkey and the amount of time it takes to cook it. Therefore, the more a turkey weighs, the longer it takes to cook. Now, this is just direct causation. A turkey's weight does dictate how long it's going to take to cook. Turkeys that don't weigh as much won't take as long to cook, whereas vice versa, a heavier turkey is going to take longer to cook. That's it for today's video notes. Thanks for watching.